Welcome to Engineering Studio with Dr. Muhammad Tahir. In this video, we are going to discuss about the shear stress distribution along the depth of beam. Shear stress along the depth of cross section for a homogeneous, elastic and uncracked beam is given by this expression. Shear stress is equal to VQ over IB. Here V is shear force on the cross section, I is moment of inertia of the cross section or second moment of area of the cross section. Q is the first moment of area about the centroidal axis of the part of cross section lying further from the centroidal axis than the point where the shear stress are being calculated. So what is this Q? We will discuss in detail. This B is the width of member at the depth within the section where the stresses are being calculated. For an uncracked rectangular beam, this equation gives the distribution of shear stress as shown in figure. So we have shear stress 0 at the extreme top fibers, 0 at the extreme bottom fibers, and maximum value of shear stress at the neutral axis or centroidal axis. So this is exactly opposite to that of flexural stresses, which are maximum at the top and bottom but 0 at the centroidal or neutral axis. To understand why we have this type of distribution of shear stresses, we need to understand the concept of Q, how we can calculate this Q, because in this equation we have this V constant for a particular section, I is also a constant for a particular section, and B is also a constant for rectangular beams. The only variable which is changing with respect to the depth of the beam is Q. So if we can understand the Q, how we can calculate the first moment of area about the centroidal axis, then we can easily understand this distribution. For example, if we have a rectangular beam like this, so this is its centroidal axis, then if I want to calculate the second moment of area, first moment of area about the centroidal axis, for example for this point, so we will consider this much. If I want to calculate at this point, then we need to consider the area farther from this point. So this much area, this much will be depth. For example, this is Y and this much is B. So area will be Y time B, and this much distance from the centroid of this area up to the centroidal axis, for example, I call it as Y dash. So that is Y dash. So Q will be equal to area into Y dash. So this Y dash will be actually, if this is the total depth D, so it will be D by 2 minus this Y by 2. So this will be our Y bar, and the first moment of area, this Q will be area times Y bar, and area is this B times this Y. And similarly, if I want to calculate the Q value at this point, for this point, so we need to consider this much area, all the area farther from that point away from the centroidal axis. Similarly, if I want to calculate the Q value at the bottom, for example at this point, then we need to consider this much area. So this area A times the centroidal distance of this area up to the centroidal axis of this whole section. So this A times this Y bar will give us Q. So if we see this Q value, if we consider a point at the extreme fiber, I make this figure again. For example, if we take the point at this extreme fiber, so in that case our A will be equal to 0. As a result, our Q will also be 0. And if I take point over here, so in that case we need to consider this much area. So we will have area equal to A1, which is this Y1 times this B. So we will have A1 equal to Y1 times B, and this much will be our Y1 bar. So Q will be equal to A1 times Y1 bar. And similarly, if I take the point over here, so we need to consider this much area. So here it will become, if this distance is Y2 and this distance, the centroidal distance is y2 bar. So our A2 will be equal to y2 times b, and q will be equal to A2 times y bar 2, and its value will be more than this value. And similarly, as we move toward the centroidal axis, so the value of q continue to increase. And if I take the point over here, so now we need to consider this much area, not the area above it. So we need to consider, we will not consider this much area, we will consider the area from that point away from the centroidal axis. So this much area will be considered. So this will be y, this one will be b, so I call it as y3 for example, and this is b, and the distance from this, the centroid of this area, this shaded region up to the centroidal axis, this is y3 bar. So we will have a3 equal to y3 times b, and q will be equal to a3 times y3 bar, right? So in this way we will calculate this q value. So as q is increasing, as we move from the extreme fiber toward the new centroidal axis, so as a result, when we will calculate shear stress, which is vq over IB, so here we have these factors constant, so only this Q factor is variable, and this Q variable or this Q factor, which is first moment of area, it has the maximum value at the centroidal axis and the minimum value at the extreme fiber. So as a result, we will have the minimum value at the extreme fiber for this shear stress and the maximum value at the centroidal axis from top to bottom, or top to centroidal axis, and similarly from bottom to centroidal axis we will have the same distribution. So that's why we have such type of distribution, 0 at the extreme fiber, maximum at the centroidal axis, and again 0 at the bottom extreme fiber. And if we want to calculate its average value, so we can calculate the average value like this, V over BWD. So we can take its average like this. The shear stress divided by BW, mean width of the beam, and effective depth of the beam.